Hi, so in this talk, we're going to be presenting the Parasol processor, where parallelism meets privacy. So just a brief overview of what we're going to cover. We're going to first start with some of the challenges in working with FHE today. We're then going to talk about how we might address some of these challenges and what the design goals should be of our solution. We'll go on to present the Parasol processor, which allows for operating over a mix of plain text and encrypted data, and we'll end with some numbers showing how the Parasol processor performs against state-of-the-art. So hopefully you don't need to be convinced on why FHE matters, but for a brief review, you can think about FHE as enabling hidden state for multi-user applications. And what's nice about FHE is that it's publicly verifiable. In terms of some use cases where FHE is quite interesting, we have financial use cases, so things like private auctions, dark order books, as well as some of the machine learning applications discussed earlier, such as private inference and private training. If we're an engineer and we'd like to work with FHE, there are really two things we want from an FHE scheme today. We want an FHE scheme that supports unlimited computation. So ideally, computation with any kind of depth possible. We also want a scheme that supports a variety of operations. So ideally, arithmetic operations, Boolean operations, comparison operations, the full gamut. Even if we have an FHE scheme providing these two properties with unlimited computation and a variety of operations supported, it's still very challenging to use FHE as a developer today. So what does the experience look like if you want to create an application with FHE in it? Let's imagine you've managed to select an FHE scheme. Well, you're now going to need to figure out what are the most appropriate scheme parameters. And you're going to have to think about things like security level, performance and efficiency, and potentially even correctness or chance of errors. You're also going to have to think about how to structure the program to take into account where FHE is weak. So ideally, avoiding high precision-based applications, multiplications, and even if you manage to do all of these things, you select the scheme parameters, you structure your program correctly, you may still have problems when it comes to thinking about hardware and how to best optimize your program for that. So the question we want to ask is, how can we make FHE really, really fast and really easy for developers to use? So we take an approach that we call maxi-min, and this is an idea from game theory. So the high-level idea is, how do we maximize our value without knowing how other players are going to behave? In terms of what that means for a solution for FHE, we want to maximize the performance of FHE, and we want to minimize our expectations of what the developer knows and their behavior. So expanding a little bit more on that, what we think is the best developer experience today is having programs where the absolute minimum amount of information is specified by the developer. So specifically, we can see this program here. This is a chi-squared program. And the idea is the only things the developer should specify is it an FHE program, and which inputs and outputs are encrypted. We also think that developers should have the ability to write in mainstream languages, so Rust, C++, potentially even Python. In terms of the code, we would like developers to use current code they already have. So ideally, they can reuse an existing application and just add on these directives. In terms of the final property we'd like, when it comes to Web3, we want FHE programs that are chain agnostic. So you can deploy this program in any chain you'd like. In terms of getting best performance, we think this means extracting parallelism. This is going to allow us to get best performance today, and it's also going to allow us to take into account future accelerators. So in terms of what we believe to be the best approach, this is a processor approach. We've chosen to go with the processor-based approach for two major reasons. Reason one is that it gives us control over how programs will be realized. And reason number 2 is that it's going to allow us to get a great developer experience. We're going to take our processor, we're going to integrate it with the LLVM toolchain, and that's going to allow us to have mainstream language support for things like Rust and C++, and it's also going to give us a bunch of compiler optimizations for free. So we've built the Parasol virtual processor. As the name suggests, it's entirely virtual. This is not realized in hardware today. We don't intend for developers to interact directly with the virtual processor. There is another layer that sits on top of it, which is the compiler, and that abstracts away all the difficulties of working with the virtual processor. This virtual processor has its own instruction set architecture, memory model, registers, and it allows for operating over a mix of plain text and encrypted data. So a little bit about the processor itself. We have our own ISA, which we've called the Parasol ISA, nicknamed PISA, and it supports all the common operations you might expect out of an ISA. We have arithmetic, comparisons, bitwise operations over any mix of plain text and encrypted data. We're also able to support branching over encrypted data via the CMUX operation from TFHE. And we don't intend for engineers to code directly in PISA. This is quite hard. So this is an example program of what it looks like if you want to code directly in PISA. It's pretty similar to working with assembly and not nice of an experience. In terms of how we get great performance, this comes from the processor's microarchitecture. And there are 2 major features we'd like to point out. We have out-of-order execution, which allows us to maximize parallelism. We also have an FHE circuit processor backend, so thinking about how do we take operations and convert it into an FHE circuit, we use a computing paradigm that relies on CMUX trees, as well as circuit bootstrapping. So high-level idea is do as much computation as possible in a multiplexer tree, and then circuit bootstrap to reduce the noise before continuing on to do more computation in a multiplexer tree. The reason for that is that it's also going to allow us to maximize parallelism. So here is some performance comparisons of how the Parasol processor performs today against state-of-the-art, and we've chosen 2 machine learning-based applications. We have the chi-squared program, which can be used for feature selection. It's a pretty simple statistical test. We also have a convolution, specifically a Gaussian blur with a 3x3 kernel. And we've benchmarked both of these processors with 128 bits of security on a 64-core machine. And we can see today that Parasol performs anywhere between 2.5 to 3.5 times faster than state-of-the-art. That's it. Thank you so much. If you want to follow our work, feel free to find us at Sunscreen Tech.